Okay, so I'm really looking forward to introducing Paul, mostly just as someone who's a self-professed systems fanboy. Paul is a low-key guy who has actually had an extremely storied career in software engineering, and to the order in which I'll share these stories. So I'll say this, that I knew this going in when I was interviewing at Temporal, and Paul was one of the folks that I interviewed with, and I knew that he was the founder of the Millwheel project, which is kind of one of the core systems that powers streaming data at Google, including like some of the search experience you get that's based on Millwheel. If you use streaming data processing in Google Cloud, that's Millwheel too. Paul built that from scratch. His name's on the paper, and I was frantically reading this paper the night before I was going to meet Paul, and I was worried there was going to be a quiz. And so it was a tough night, and I was not that well rested for my interview with Paul. But I skated by. I think he was charitable with me as a product person. So Paul made all kinds of impressive contributions to Google, like Millwheel, but where he spent more of his time was at Amazon. And the longer I've been at Temporal, the more I've realized much of the origin of Temporal actually traces all the way back to a lot of work that Paul was doing at Amazon, going all the way back to the early 2000s. And if I see you guys at dinner tonight, pull me aside, like the origin story of like how eventually work Paul did through kind of a fortuitous chain of events 20 years later has turned into what we're all talking about here today is pretty extraordinary. But the shorthand story is that Paul played a really essential role at Amazon in terms of breaking up the biggest monolith there was at the time, which was the Amazon website itself. In the process, he made a bunch of foundational contributions to the way Amazon was built and run, and many of those eventually became what we came to know as Amazon Web Services. And Paul also is another example of someone who came to technology later in life and still wound up having a prolific career. He was at one point in finance and CEO of a bank, so it proves that there's hope for us all. And with that, I want to introduce Paul Nordstrom.
Hi, everybody. Thank you. Charles has actually done a part of my work for me because part of my talk is actually about exactly what he was saying, how the systems designed at Amazon led forward. But I'm going to do a little more in-depth version of it right now. So I've been lucky enough to work on some of the most widely used systems in the world. And right now, my current plan is to add Temporal to that list. So I got volunteered kind of late to come give this presentation. Oh, wait, we need to make sure my... And so I'm looking for a topic, right? And I talked to some people, and they said, hey, service-oriented architectures, it's pretty big, and you were right there in the middle of it. That would make a good topic. And then, Group was the name of the general architecture at Amazon that my team designed and built. It basically brought Amazon into the service-oriented architectural world. I'm just going to say SOA from now on. So I started thinking about that, and I started thinking about the parallels between what we did then and what's going on now. And there was a lot of that. So, and then I took another step back, and I started considering the system design evolution as a whole, across longer and longer timescales. And I ended up with this non-working flipper. Fortunately, we have a backup for that. OK. So this was my topic. So have you ever started a PR? You're just going to change one little function, and soon it's got 37 files and thousands of lines of code in it. So you have to back off from that sometimes, too. So I decided I'd have to back off from this topic. Plus, how would you even start it? The only thing you could do with the start the universe off, OK, this is... Now neither of them is working. OK, this one's working. Life users, what's the beginning? OK, well, if you're not a programmer, you might recognize, but that's the Big Bang. So I pulled pretty far back, where I belong, into a talk about software organisms. OK, why software organisms? I realized that systems aren't designed. We don't do software architecture. We do software evolution. I've been in the architectural field, okay? I've done a lot of building, in fact. And architects do this. They write down an exact plan for a building, and then they hand it off to somebody, and exactly that building gets built. Right? That is not how software is built. Software evolves, it's put together, it's jammed together. I'm going to talk about that process from my personal perspective. Plus, I also love thinking about big picture things. I don't think anybody's too surprised here that I took on a very large topic. I'm not afraid of that, but we're just going to have to bear with me because this talk got done in a few days and I haven't practiced it very many times. So, I'm thinking about parallels and evolution, and I realized that when I started programming, this is 1973, okay? I'm old. That's pretty far back compared to most of you. In 1973, in my school, there were 0 computers. There were 0 computer science or computer classes, programming classes. I took the very first student in the very first class. My teacher had never written a program either, okay? There was 1 computer in my entire town at the local college. And so the high school invested, they said this is the future, right? They said they invested thousands of dollars in computer equipment. What did that get them? A teletype with actual keys and typewriter keys, right? Audio coupler, 12 characters per second, and a paper punch reader and punch. You could make the typewriter go by whistling at it. It would type. Try that with your monitor, okay? So it was, like I said, 1 computer in the town at the local college, but I wanted to learn how to use it. So at this time, even though in my school and my town, things were pretty backwards, this is 73, this isn't 50, there was a lot of computing infrastructure out there, okay? It's like this diagram, a bunch of parts. So we're only about 3 billion years ago right now, okay? Don't worry, we're going to move ahead rapidly. The systems world is lots of parallels, but it moves ahead a lot faster, fortunately for you guys, okay? So it's like this primordial soup of components that life was at the early days before cells, right? Life was just jumbling these parts together, and eventually cells started to form, okay? So it was like this, like I said, a soup, but in the computer world, the soup was alphabet soup, of course. So all the pieces that were out there, we just started throwing them together into programs, trying to make something useful. And nobody knew how, or there was no design to this. We just tried things and they worked. And the things that worked, we did them again. And the things that worked well, they reproduced. So this was my first program. It was a little blackjack program. We started making things that were useful, assuming you consider blackjack useful, okay, for some value of useful. But it was, like I said, it was evolution. Things just kept growing faster and faster. Algorithms grew, DNA, it was like the DNA of computing. Okay, ECC codes, other kinds of coding, sorting, hardware, every kind of thing. And so more and more of these little cell programs grew, and they copied, and they got really useful. They paid my way through college. I consider that useful. So one of the first things I did when I went to Northwestern was, approach the people about, is there something I could do that would, I was broke. So I wrote a program that let the university graduate school decide how much to loan each student in their classes, right? Student aid it projected your economic income for the future and protect your expenses and took your family wealth, right? These were useful things, but there's still these single cell programs. Okay? So, jumping forward a decade now, we're going to move really fast, like I promised. The cells got bigger and bigger, and the environment for building these cells got richer and richer. So we really were building pretty big programs, but they got out of control. They grew into amoeba. I mean, this is a real picture of an amoeba, right? It's this jumbled, gigantic mess of biological components, and I'm going to call this particular, I gave it a name, Amazonia obidosea, okay? I ran into this amoeba when I joined Amazon, okay? Obidose is the program that at that time, 1999, Amazon was using to deliver their website, okay? So you went to www.amazon.com, a request would go to Obidos, and a giant piece of machinery, all in one big process, would start running and produce your, it was like a biological junkyard. And it contained so much code that most of the machines in the company couldn't link it. And if anybody introduced a change to it that broke it, the whole company's software development shut down until that problem got fixed. So this was right when I joined Amazon. I said, okay, this is not working. Somebody needs to take this problem on. And I had, had nothing to do. I just joined the company. So I had an idea for a different approach. Okay, something more distributed. I had built systems before in the trading, the financial trading world, where there were pieces of the system, but I wanted something with a more organization to it. So my first drawing looked like this. Okay, I'm going to have the little g in the Pentagon. I called it Garupa. You'll see why in a minute. Okay, it would talk to a shopping cart service. It would talk to an item service. It would have databases and templates. Okay, this is almost identical to my first drawing of Garupa that I did in early 2000. And I called it Garupa because I looked at the map of the Amazon. This is the Amazon River. Okay, and it was this beginning of the branching of the river as it approached the ocean. So it's like, that's kind of the concept I want. And at Amazon in those days, all systems were named after a city or something on the Amazon River. Okay, so this was the Garupa architecture. And it turned out, we explored it into existence. Again, we had to take the existing components of like computer components, analogically like biological components, and turn that into pretty much what you see in this previous picture. A orchestration engine called Garupa, a set of libraries for building applications, for building the services that are going to talk to Garupa, and also for building Garupa itself, tools for configuration, debugging, consistent tracing, metrics, and just as importantly, a contract between the services and the people calling the services. And that was really critical advancement in the system of these times, right? Instead of one giant binary, we had teams working on individual components, but they had a contract and they knew what they had to do. So if you think of this as one big architecture, which it was in my head, right, even though it was separated in the code library into separate pieces, it added a lot of regularity to Amazon. Okay, things that every individual team had been doing just individually, building themselves. It was really it was a pain in the ass, okay, to write software at Amazon. This changed that playing field. Another interesting thing is that Garupa actually was a program without business logic, and that was new to the world at the time. It was an orchestration engine, but without any logic about what it was orchestrating. All it knew was read template, follow rules, talk to services, right? So you can see where I'm going with this, right? So it also had a whole lot of limitations, okay? This was primitive. This was a very primitive service-oriented architecture, okay? But it had one. For example, it only operated in synchronous mode, right? You ask it for a page, it would go generate everything and would get back all the results and it would compose that and return the page. There was lots of limitations to this thing, but it did have the abstraction of a platform, and I care a lot about abstraction. So Garupa evolved into an empty screen. Okay, there's a picture there, which is not showing up. All right. It's not a very important picture. So, Garupa, the orchestration engine, foundation library, tools for configuration debugging. We've talked about most of that. And there's the evolved Garupa, right? So, this became, okay, this was one of the key points of my talk. This is the evolution from single cell to multi-cell. Okay, in the real world, in the biological world, the evolution for single cell to multi-cell set off a giant chain reaction of evolution and productivity, and unimaginable things grew out of that ocean the minute that cells started to combine. The same thing happened in the systems world, engineering teams got decoupled. And just as importantly, they gained autonomy. They could be responsible for their own stuff, they could own it, they could build it, and they didn't have to, right? That changed everything, right? There was only one of the many changed everythings, though. We got a previously impossible degree of reuse and portability, okay? Operability. And not only of the systems, but of the engineers themselves, because once you start working on a platform, you can work on another team who's using that platform. So both the system DNA and the human DNA got very transportable within Amazon. And that was pretty important. And then lastly, these platform systems just took care of all sorts of crap, really annoying crap. And you can never underestimate the power of less crap. So in the biological world, this is called the Cambrian explosion. Okay, some people call it the biological Big Bang, but I like the Cambrian explosion because my ancestors came from Cambria. So I think that what's happened in the systems world, sort of, like I said, in my imaginary postulation to you guys, since this service-oriented architecture is equivalent to the Cambrian explosion, right? Look at the amount and number of how the way computer systems have pervaded our lives in the last 20 years. I think it's enormous. Okay, it also produced some really lovely monsters. Okay, so what's next? Here we are. The world has exploded, but everything's still living in the ocean, right? But they're starting to crawl out onto land. Okay, just like all the early service-oriented architectures were inside of data centers owned by companies. It's hard to even imagine right now, but that was it. You had to have your own data center. You could lease data center space, sure, but really you had to have your own data center to run your own programs. Right? So the service-oriented architecture and something else, which was a conversation Jeff Bezos had with the team of engineers, the senior engineer team. He's asking this question, can we take the service components that we've been building for these years and sell them to the rest of the world so that people who don't have their own data centers can build software, right? This was one of the most amazingly visionary questions I've ever heard in my life. Because this was, honestly, it's really hard to look back and know how out of the box this idea was. It was enormous, right? So just like the ocean, the creatures crawling out of the ocean, systems started crawling out into the land and sky, and even to the clouds, right? So, and this is what happened. This tree of life is the explosion, not just in the ocean, but across a huge landscape of a realm of deployment opportunities you can think of as for the animals. Economic opportunities, functional opportunities, this huge space to fill up. I don't think we've seen even a significant fraction yet of the impact of the combination of cloud, service-oriented architecture, and of course advancements in all sorts of other areas, hardware and so on. But I think it's mostly the software. I think it's mostly you guys. So this is still day one, Jeff Bezos loves to say, and I think that's perfectly appropriate. So for all the people in this room, the cloud's pretty important to our lives, right? So I want to talk a little bit about the cloud evolution and how it proceeded and how it's impacting us now and how it might impact us in the future, because making good decisions requires at least a little bit of looking forward. It certainly requires understanding. So the first kind of thing that happened is, Sergey mentioned to me, so the correct name for that, Paul, is lift and shift. Okay? Taking existing architectures that's like system DNA that's been running inside a data center and just deploying it into the cloud. So that's a very valuable thing because it opened up opportunities, or more economic opportunities than like biological evolution, but it's still very important progress for our world. Slower and more important is the new evolution, the mutations, the biological growth of completely new products designed for the cloud. And that's still basically just getting started, right? In fact, Temporal is one of these. Temporal is one of the companies that has taken something that is really makes sense for the cloud and probably didn't ever make sense for a closed architecture, for a data center architecture. So obviously one of my goals here is to tie Temporal into this conceptual framework. But Temporal, to do that well, I have to talk a little bit more about the tree of life again. Because Temporal is a very specific kind of computing organism. So let's figure out how that works. So we're going to go back in time a little bit to the early days again, and look at operating systems within the realm of computer software, like DNA, right? Between the evolution of software organisms. So operating systems basically do one thing. Okay? At the very beginning, all they did, literally no abstraction, they just hid the hardware from you. Okay, that's not literally no abstraction, that is an abstraction. You want to treat a file as a collection of bytes, not as disk platter spinning. Do you guys still know what a disk platter is? Okay, probably some of you don't. You don't care about the frequency of the light in your fiber optic lines. There's lots of things you don't care about. This operating system's there to hide them from you. Okay, it's there to provide abstractions, convenience, and speed to your development. And I heard one of the earlier speakers talk about the speed of development. It's critical, right? So there was some evolution here. Okay, for instance, we've evolved from disk platters to the abstraction away from a disk platter to a collection of bytes that we call a file, right? To RAID arrays, right? You can still treat the RAID array as just a disk file, but it's got a lot of characteristics you care about, durability and reliability and so on. And then abstractions for multi-tiered storage, right? Cold, warm, hot, right? That's another abstraction that the operating systems of today can give you. And that's just one niche. There's lots of those. But I still feel like, and again, I get to say this is my personal perspective on things, that today's operating systems still are just hardware abstractions. They're designed for a single machine. They don't touch the potential of cloud. They don't really know about cloud. We have other components that we use when we need to think about the cloud, like Kubernetes. It's not in the operating system. So it doesn't, and they also haven't changed really that much yet, well, except for the people in this room, how you design systems, right? We're still writing programs, and then we're running a bunch of copies of them. And you still have to think about a bit about the hardware and the memory and CPU and stuff like that. I want to see that stuff abstracted. So, and we have made advances in the understanding of these abstractions, right? We have, like, I'm going to call them system genes, for more advanced kinds of storage, like a relational database, for PubSub, for communication paradigms, for computational abstractions like the mill-wheel architecture. But I think they're poorly integrated today. And I don't think that the operating systems today do nearly a good enough job of hiding the complexity of using them. There's no consistency between them. You have to learn a new paradigm, new APIs, et cetera, for every one of these abstractions that you want to put into your system. So the reason that I haven't changed the slide in a while is because I don't think the operating systems have evolved nearly enough. Okay? I'm proposing that we should think harder about that, and we should do something about it. I want to take the abstractions that I just described, PubSub, relational databases, and a lot more programming abstractions like error handling and versioning and stuff like that, turn them into operating system abstractions, okay, and put them in an operating system that I call the semantic cloud operating system, right? It should be able to speed up your development, maybe give up a little of your power, if you will, at the deep, deep end, like a device driver does for a disk. But you should be willing to give up that power because you get speed and you can build things you couldn't otherwise get done. You don't really want to write another logging system, do you? Okay, so the other thing I call a semantic cloud operating system is temporal. So these are, you're not expected to read this slide. I put it up because every talk should have one slide with actual real content in it, okay? But these slides will be published, so you can come back and look at this. These are the kinds of things I've been talking about all along, and I'm not just going to read them to you, okay? But these are all I could think of, not being all of them, but a pretty good set of the really important abstractions that as a programmer you shouldn't have to worry about, that should come packaged with your operating system, should work for you automatically, and will make you a dramatically more powerful programmer, okay, developer, whatever it is, designer, systems, I do want to call out one of them, the first one listed, the durable execution, because that is one of the most important innovations that I've seen in all my lifetime of systems development that Max came up with as part of the temporal system, and I think it's one of the things that sets temporal apart from everything else. It's the critical thing that you can write code and know that it doesn't matter if any step of your code fails because it's been durably persisted. It doesn't even matter if one of the steps of your code has a bug in it. We'll stop there, let you fix the bug, and it'll carry on from there. This is an unbelievably beautiful abstraction. It's one of the things that made me come to temporal to work because I want to turn that into the thing you're seeing in my talk, really, which is an operating system that encapsulates that plus all the other crap that I'm tired of dealing with. So these aren't new concepts. Like I said, a lot of this is packaging. That's how evolution works, right? The genes evolved, and something evolves a finger, and suddenly anything that needs a finger, the genes get transferred between organisms much more quickly in the software world, and suddenly everything has fingers, right? So I think that the benefits of this proposed rich set of abstractions are going to be similar, in fact, to the explosion we saw from the abstraction of the service-oriented architecture, because you'll be able to get done so much more easily, much faster, better, etc. So this is the road I say temporal is on today. Okay, I'm kind of up to the present. It's a new and different level of operating system abstraction. The next part of this is going to be much more speculative, okay? So it's the future, right? To talk about my next proposed sort of vision for how evolution is going to carry software systems forward, okay, we have to take a couple little side trips like I did at the beginning for the family tree. This is about language. We didn't invent language. Birds have languages, bees have languages. Those are all languages. They're not as powerful as human language, but they're still languages. Languages aren't architected. They're not designed by somebody. They evolve too. New concepts come into language, and we invent words for the concepts, or sometimes we invent concepts for the words, but we progress down this road of richer and richer abstractions in the language, right? There's a parallel here too, right? So I believe that at a certain point in the time, in the past, that language crossed a boundary, okay? I don't have a good word for that. A dramatic change in the system can come from a small change in one of the conditions, right? In physics, it's a phase transition. You change the temperature of the water down by 1 degree, and suddenly you have ice instead of water. For me, that's the power of a combination of factors come together, and they make important differences. I think that as the human language evolved, new abstractions, human abstractions evolved, and it converted humanity from what I would call an ecosystem into a community. Okay? What's required for a community? A community is not the same as an ecosystem. Two bacteria in a pot is an ecosystem. One of them's feeding on the other, right? A community requires a form of communication between the people in it. In fact, I would say it requires that they depend on each other by agreement. That's what makes a community real in the human world. And if you think about the earliest human communities, they started out as hunter-gatherers, right? And they evolved into these small communities like I've pictured here, and they would share in the protections of the infrastructure. They could specialize and contribute their special talents to other people who had different special talents, right? One person could grow corn, one person could make shoes, and suddenly both people have corn and shoes. And they're both richer for it, okay? So communities in the human world, as soon as they became introduced, which I claim is, language was a requirement of that, they spread across the human world like mad because they convey a survival advantage. So, oops. This is where I'm going to get out my magic 8-ball and say, I think that the next major advance in the systems evolution is going to be similar to the one I just proposed or just called out from biological evolution. Okay? I think we're going to form system communities. Okay? What would make a system community give it survival characteristics, give it a survival advantage? Nearness or interoperability of services hosted by the community, lower latencies, efficiency matters, reputation, if you could count on other services in your community of services as having a reputation that you could count on, and somebody's measuring it, let's say, reduced probability of fraud, and let's not ever forget the importance of the network effect, which I haven't talked about much in this talk, but it's sort of been there in the background, because network effects are critical. And in the communities, what happens? Somebody who had a special talent, iron, like a miller who had special skills, would go to the best community he could because he'd get the most value out of his contribution. He'd get the most value back from the other members of the community. So choosing the right communities is important. And of course, suddenly that community is even stronger, right? So communities have this natural growth thing that happens, okay? So I want to be part of that kind of community. So how do we get from today's ecosystems to system communities? Well, I sort of led you there already. I think that we need an appropriate language, but it's not a human language we need, it's a systems language. So I propose that the catalyst for systems communities going forward would be to give our systems the ability, or give us the ability as writers of our systems, the ability to express semantic concepts about the systems. And so Temporal is starting a new project, okay, with this in mind. Okay? The point of this project, the name of this project is called Nexus. So the Nexus vision is to create a language, a blueprint, if you will, to describe services, so that machine-readable language now, so that services can know what another service is capable of, and how to interact with it. And there's a long list there, right? So is it async or sync? Is it a arbitrary length operation? ALO is one of the Nexus things vocabulary that's important. Does it provide subscriptions for events? Does it have reliability? Okay. And then even if you can describe that service, well, okay, here it is in a file. Maybe it's just, how does it work? How do systems talk to each other? So Temporal is going to build the adapters that let's say, a workflow talk to an HTTP service without knowing it's an HTTP service, gRPC, whatever. Okay. When of course there'll have to be code that you can write to make this make sense. We're not taking the code out of your hands. We're just empowering them we're giving them bigger hammers to hit things with. And I believe that this is going to lead to another giant growth in what you can do, what you can build in your systems. So again, back to my little refrain. This isn't really, most of the stuff here isn't new stuff. It's stuff that we already have the abstraction for. Okay, that's how we work this. First we figure out how to do it, then we create an abstraction for it, then we have a language to describe it, and then we integrate it and package it. So we're taking another step forward in this sort of 3 billion year journey, 30-year journey to take systems to the next level. I don't know what's going to come after that. I haven't even thought about it. But I do believe that this is, again, going to change the world of systems, okay? And I'm not asking you to believe that, because the benefits, if we do a good job on Nexus, the benefits aren't going to be you have to believe in the community. This is me talking at my little TED Talk almost. The advantages will be immediate to you. You'll be able to sell your service to other consumers of it that want that functionality. You write a bank transfer service, you'll be able to offer it to a wider group of people, anybody using Temporal, or other platforms. We're not going to make this proprietary. We're going to make this a very standards-driven thing. What matters to us at Temporal, what we're trying to build are tools that you can use that make your job easier, faster, better right now. And this is the next step, one of the next steps we're going to be taking. So one of the things I wanted to leave you with is that it's not the perfection of this analogy that matters. I think this was kind of a fun. I really appreciate the opportunity you've given me to do a little big picture thinking about something that, normally I'm very heads down in my code. It's really fun to take a step back and think about these big picture things. I hope they've been interesting to you as well. Okay? But I'm not asking you to agree with me. I'm just hoping that I have opened up intellectual pathways, maybe introduced a few mutations into your mental mindset for how you think about computer systems that will take you down interesting roads as well in your thoughts about system design. I think that 20 years from now, it's kind of interesting that he introduced me with the 20 years ago, because I think 20 years from now, you're going to be looking back at this conference and saying, remember that first Temporal conference where we talked about software communities and stuff like that? Look what Temporal and all of the people using it, at least the Temporal ecosystem, hopefully the Temporal community, look what it's grown into. Because I think it's going to be as big as the service-oriented architecture world or bigger than Amazon. So thanks for providing the audience for my little twisted imagination path here. I hope you enjoy using our tools. I'm happy to, I love communication and I'm interrupt driven. So you want to write to me, Paul at Temporal, feel free. I'm happy to answer questions or to talk about anything. I talk too much, but that's okay. These are my ideas for Temporal. I hope to also, I care a lot about not just working for my paycheck, but also making the world a better place. In fact, that's why I went to Amazon originally. You can shoot me for that one. But it's also why I went to Google. Well, I was in the financial markets, okay? Which is just sharks eating other fish, right? At least Amazon was producing a real value into the economy. Okay? I went to Google because I wanted to build a tool that scientists could use to do research on continuous problems, okay? And Google was the only place I could build such a tool. I'm doing the same thing at Temporal, building something that's going to make the world of computing a better place. So that's it.
Thank you, Paul. And we got the Slido Q&A back up, so feel free to ask your questions. And I'm gonna start with one or two. I just want to go back to that the very beginning of this origin story at Amazon, and you said that you kind of moved to this new architecture, at least for parts of Amazon. But before it became Amazon Web Services, there's this lore that goes on that there was this mandate that kind of went out, like inside of Amazon proper, where it sort of said, well, we're all going to be this way now, and everyone's got to kind of implement this way. So could you just talk a little bit about sort of how did this go from like a way of refactoring out of kind of this initial kind of single monolith that Amazon had, and how long did it take from that to start showing success until when it was more of like a standard way of life, or was it, or did people always get to vote with their feet?
That's an interesting question. Because it's so complicated to answer. There was not a universal buy-in, and I didn't get swamped with applicants from my team when I proposed the service version of the website architecture. I was lucky though that the the management at Amazon believed in me, and they bought the framework I had designed and written at my previous company. So I had this huge leg up. It was just a piece of the application architecture. It wasn't the service framework that came later, but it was this thing called the Foundation Object Library. It was patterned after NextStep, actually. It was a C++ implementation of NextStep. So, but it had a beautiful model to it, and all of the existing code at Amazon at that time was just jumbled mess. It was called This Old Code Base, TOCB, and it had no dependencies, no nothing. You linked in, you tried to build Amazon, you got the shipping department stuff. You tried to build the shipping thing, you got all Overdose built linked in. So, in terms of getting the teams around, centered around building in this fashion, I would say it was sort of a leapfrog kind of thing where a couple of teams tried it and they were very successful with it. It turned into what Jeff called this two pizza team thing. Once the service, so that was about 5 years in though.
Oh,
was the mandate?
Right? The kind of two pizza team.
Yeah, that came after the whole architecture had been proven and we'd switched completely out of Overdose onto Garupa, and because you couldn't work in a two-pizza team. You couldn't keep teams in that way in the Overdose world because the software you were working on was such a jumbled mess. The teams were also a jumbled mess. So that's sort of the evolution of the internal development structure of the company followed the evolution of the software itself.
That makes sense. And then obviously you were a big part of how this happened for Amazon proper. But from your vantage point, as this got turned into Amazon Web Services, it's not like the first day everyone got a like-for-like experience compared to what people had inside the four walls of Amazon. What struck you as different? I think the thing that's been interesting to me is it feels like it feels like everyone's interest in services and microservices, at the same, really happened after the infrastructure of Amazon was made available. The outside world, until they had that infrastructure, the number of people that followed this type of concept was a much smaller population. So as you watched Amazon kind of expose the first tools, but maybe not all of them, what do you see as the difference between how people wound up using Amazon Web Services versus the life people had inside of Amazon, if you can remember?
Well, I talked a little bit about this in my talk, actually. Most of what happened for a pretty good chunk of time, maybe even a year, after the release of AWS was just the lift and shift stuff. So they weren't thinking in the way you're talking about of shifting their design approach until considerably later. So the first thing that happened was people just took applications they were running in their own data centers, put them in the cloud, or ideas they had for their own running. They didn't have a data center, but they already had the sort of the conceptual program. The genetic shift hadn't happened yet. I was really deeply involved in the Amazon world at that point and not so much focused on what other people were doing with our tools. So I don't have a good answer to your question that I saw clearly when did the transition in the AWS world happen to a more multi-cell kind of approach to software.
Excellent. Okay, so this is another interesting one. So there's a question from the audience. It's about analogs to Nexus, or kind of, and the question, I'm going to take the question literally, and then I'm going to add one more on top of it. The question was around how would Nexus compare, or how would cross-service communication compare with the efforts to do blockchain using digital contracts? So kind of like a different way where there's this loose coordination. And then I'll throw on kind of another, an older one, which is if you look at the old object request broker standards like COM and DCOM. So two different analogs. What's right or wrong about that analogies when people think about something like Nexus?
Well, so the first one, the blockchain kind of stuff, that is, I put that in the same category as I did before for the different kind of communication abstractions that exist and that don't have an operating system around them, but the abstractions exist and the capabilities exist. And so like PubSub or like Kafka streaming or whatever you want. It's a brilliant innovation in my opinion, but it's in a sense, it's just like a new creature that evolved and now it's out there running around and it's popular, but it's not that tightly. And certainly it took advantage of some of the genes of the service-oriented architecture. They needed those genes to build the blockchain approach to their problem, but it's a and it's a nice general solution to what could have easily been a very specific problem. So like I said, I'm excited about blockchain as an abstraction I haven't had an opportunity where I needed it in one of my systems, but I would love to incorporate it in the temporal operating system, in fact, in the long run. What was your second one?
What about something like Corba or Com,
Corba,
which is kind of another
the identity-based, which Corba is an identity-based thing. You have an object and you perform operations on it. And that's just not as general as an abstract one. You can use an abstract request reply, abstract service and abstraction to implement Corba, but you can't really go the other way around, okay? Because you don't have, Corba requires an entity, and you create the entity. Now that applies to lots of problems. It was a fine thing at the time, but it never evolved into something widespread because of its limitations, if you will. When you have an abstraction like that, it forces you into thinking in terms of the abstraction. That's what abstractions are for. They're abstractions for how you think about problems. And Corba forces you to think about a problem in a certain way. It applies to lots of problems, but it wasn't a general enough approach. And because it had this sort of centerpiece of the object, common object request broker, it didn't naturally evolve into something that was general purpose to become an operating system.
It kind of presupposed a very specific programming model.
Yeah.
That makes a lot of sense. And then okay, so I'm jumping around into the questions here. But so another question we got was, actually, I want to get to the one. Okay, so you mentioned this briefly, but just to kind of expand on, you said at some point, well, we don't want to make this notion of Nexus proprietary. We wanted to make it more of a standards-based thing. And I wonder if you could expand upon that a little bit. The question specifically was, are there any thoughts as a part of Nexus to collaborate with other workflow or orchestration projects to create standard primitives that work across engines?
Well, it's a much better question for Ryland than it is for me, because Ryland, as you know, is the one who's really working on Nexus right now. But I think, I've had enough conversations with him about it to say that I feel like our goal here is to create something that's standards-based, but maybe not interoperable between platforms, but interoperable between different customers. It's hard to say this, right? It's the very beginnings, and it's very early days, and it's not very well fleshed out. We certainly, in fact, we already have started collaborating with other temporal customers and helping us design how the Nexus thing will serve their needs, right? And there's certainly pieces of it that are going to be proprietary, but there's nothing preventive. If there are two communities, let's say, if you think of Nexus as the basis for community, like I do, okay, and there are other communities, it makes absolute sense to make those communities interoperable as well at some point. That would probably be just like, again, I love the biological analogies, two communities that formed, eventually start trading with each other. First, the communities have to form, but then you start reaching out and forming connections between them. And I suspect that that's what will happen in the Nexus world, that Nexus will get, turn into something valuable to the people in this room and then their followers. And then later on, if somebody else builds something that's comparative and valuable to communicate with them, we'll make them interoperate.
I'll actually, if it's all right, just a little bit of color, because I am somewhat familiar with our plans here, and say that we care a lot about being able to make this Nexus pattern workable by many platform technologies that are not just temporal. I don't think that we believe that the way we achieve that is by having every primitive in the temporal programming model have some translation to function identically to some primitive in someone else's programming model.
Right.
That's not the interesting part. What's more interesting is that you can implement a service with temporal, and then someone who implemented a service some completely different way can talk to the service to implement the temporal, and there's some way where they handshake with each other and where they can understand certain semantics from one another. So it's much more the handshake between two services. That's the piece that we want to be as open as possible. But given how nuanced the programming, the decisions are within the temporal programming model, very unlikely we could say, oh, we're going to create some
your workflow code is going to work on temporal, or
this child workflow is laid out. Oh, it's going to work in the same way when someone else uses the child workflow, but they call it something different.
Right.
That's less interesting than what we want is that you can call or be called as an arbitrary length operation, and some other batchy QE or orchestratory thing can be the basis for that, but you don't need to know what it is. That's going to be my paraphrase. Okay, more tangible question. Nexus. Let's see here. When communities become cities, security issues grow greatly. There's so many side comments I could make there. How do you see this informing next steps if community members stop trusting what follows? It's a great question.
Yeah, it's actually, I had a line in my speech that I removed because it was too complicated to talk about, but I have thought about this question. Mm-hmm. I think it's a really interesting one. So there's one question. The first question is, does the analogy break down when you go from small community to big city if you're talking about system communities instead of human communities? You know, the reason, my opinion is the reason that happens in the human communities is anonymity sets in. When people don't recognize you down the street, you're free to do something really annoying and obnoxious, okay? That's not going to be the same, or maybe not even the case in a system community with thousands of systems participating. Mm-hmm. Because systems don't, they recognize everyone. They can recognize 10 other systems as easily as that 10 million other systems. So I'm not sure that the analogy holds that the cities of the systems communities, if we grow them as I'm proposing, will run into this problem. It will probably be a different problem, is my guess, mm-hmm. Okay? And that we will have just as good, arbitrarily speaking, I could say it could be less of a problem because systems can do pattern recognition, but you need data. So larger systems have more data and make it easier to recognize, let's say, bad behavioral patterns and detect them and oust them. So the answer is we'll see, but I think it's a great question, but I actually believe that it's worth thinking carefully about before you start trying to solve a problem that might not exist.
Framing. Okay, let's see here. One kind of very practical one. How will the need for backward compatibility slow down Nexus?
I don't think that's actually the biggest problem Nexus is going to face. I think that, we're opportunistically adding features to let's call it like I do, the temporal operating system that let it interoperate with other systems. And there will just be limitations, if all you have is an HTTP REST service out there, right? Being able to call them at all is a step forward. And today you can't really call that from within a workflow, certainly not trivially, certainly not in a clean and supported way. So, I mean, we're building the backwards compatibility in a sense as we go. And we don't have the operating system baggage of a Windows, and DOS, compatibility, those kinds of things, because we're at a higher level of abstraction, and backwards compatibility are usually in the implementation, not in the abstraction. So mm-hmm. We'll see, but I would forecast that that's not going to be, again, our hardest problem to solve.
Yeah, just adding a little color there as well. Not that they're identical problems, but Temporal has actually maintained backward compatibility successfully between the client and the server for a great number of years at this point.
Yeah.
So it's, like you said, it's an implementation discipline more than it is for us, or an engineering discipline for us more than it is an abstraction problem. Okay, so we have time for one more question. Okay, so. Actually, in the most popular question, so Nexus sounds like a successor to SOA.
To what?
To SOA, service-oriented architecture. What do you see or hope will happen to the organization or the layout of engineering organizations as a consequence?
I don't actually think of it as a successor. I think of it as evolution, right? It's a more capable evolution that is congruent in the sense that it doesn't require reorganization to move from SOA to a system community, a Nexus world. Mm-hmm. The participants have to evolve, but the organization is already, the small groups of engineers, there's nothing better than a group of like 4 or 5 engineers. There's nothing they can't build if they have strong enough tools, right? So we're giving them even stronger tools to build even I don't think we're going to change the 5-person, the 2-pizza team into something different. And I don't think we're going to need to change the companies into something different because they're kind of already know the power of these small software development teams. So, mm-hmm. So I think it's going to work out I think it's going to work out easily is how I would characterize it.
Yeah, it's like the inexorable march is that the application domain keeps getting broader and broader and broader, but the teams, like the accountability of the team, it gets like tighter and tighter and tighter. And this is kind of an abstraction that makes that more possible.
Yeah, it just makes it more powerful, yeah.
Yeah, very cool. It was an excellent talk. Thank you so much.
Thank you.